Hey everybody, welcome back to the first seminar of the winter term this year. Good to have you all. Two new arrivals, Antonio and Julius, two PhD students who will be starting. And Thomas, who has arrived, I guess has been here for a while, but this is maybe your first official seminar. And he will give a talk at his first official seminar on the Durdevich approach to quantum principal bundles.
Great. Thank you, Ray. Yeah, it's a pleasure to give this talk here. It's also quite nice that there was this pre-seminar, so there was a lot of motivation, and basically I don't have to do much anymore, right? So, but still, I would like to spend some minutes on motivating what we are doing. So yeah, let's start here with this slide. And so the idea is kind of this, that if you want to do physics, like differential geometry is our friend, right? So we can do gauge theory, we have principal bundles, and all of this is pretty nice. The problem is that as soon as we go to quantum physics, a lot of this is breaking down, and we really need a radical new way of thinking about the mathematics that we are using there. And so that's why I have this slide here that tells us that while on the classical side, if we start with a physical system that could be some smooth manifold, in the quantum picture, in general, there won't be any topological space, so we cannot think of functions on something. So maybe we can start from just an algebra associative unital, and maybe later on we can add more things to it, like we can think of C-star algebras or spectral triples or whatnot. But for the moment, maybe we can start just with an algebra and see what kind of differential geometry can we do there. So the first thing one would do in classical differential geometry would be looking at differential forms. So we have the cotangent bundle. And this on the algebra side, on the quantum side, would be just a differential graded algebra that is maybe generated in degree 0. It would be A, just like we have seen in the previous seminar. Symmetries on the classical side will be some Lie group action on our system. And on the quantum side, we don't have Lie groups anymore. We will have Hopf algebras. And since their arrows go in the other way around, instead of a right action, now we have a right coaction. Yeah, so this is this operation here, delta A going from A to A tensor H, satisfying the dual axioms of an action, just we have seen in the pre-seminar. And then a principal bundle in this language. Okay, first of all, in differential geometry, we all know what a G principal bundle is. On the algebra side, what we get is a Hopf-Galois extension. So there we are looking at B, which is the subalgebra of elements that are invariant under the coaction. And then there's this canonical map, chi, mapping from the balanced tensor product to A tensor H. And here we just asked that this is an ISO. In this case, we call this Hopf-Galois, or in a different language, one could say this is a quantum principal bundle, QPB. So here we just ask this map that is written here. So basically just using the coaction on the second entry here, multiplying everything. If this is an ISO, we call this a quantum principal bundle, which classically is the same information to having a principal G bundle. Okay, that's very nice. So in this talk, I'm going to speak about the work of Durdevich, and this is something that one could call maybe partially lost literature, because even though those papers here, they are from the 90s, yeah. I talked to several people working in the field, and it's not that well known. So the papers are not cited a lot. So and even some of them, as you can see here, are not even published. So they are just archive versions. Oops, I didn't want to do this. So what we did in this preprint here is we were just having a look at these old papers and trying to see what we can get from it, like writing down things in a more modern language, clarifying some parts, and yeah, what we found was quite interesting. So I hope you will also like it, and this is what this seminar will be about. Let me also mention something that was missing in this work is Đurđević was mainly caring about the classical picture. So just saying, okay, so this works very well in the classical setting, but he was not worrying too much about examples. So those were missing in these papers. So what we did, and what we'll also see at the end of this talk, is give a lot of cases where something interesting happens in the setting apart from the classical, like in the true quantum setting. So we will see the torus and many other things. Okay, so this is just preparation. So let's, okay, more preparation. So just to summarize what we are going to see, starting from a quantum principal bundle written in this language, what we will do is we will give differential calculi for all of these algebras. So on the base, here on the total space, and on the structure Hopf algebra. But since we have seen that there are many different choices, we want to take some differential calculi that are meaningful or interesting. And so we want to do this in a way that the differential graded algebras we get form again a Hopf-Galois extension, so that you can kind of see this as a functor from algebra to differential graded algebra that preserves the property of being Hopf-Galois. Furthermore, we will get an Atiyah sequence, the one that we have seen in the previous talk. And we will also get a canonical braiding such that our differential forms have some braided commutativity. So this is really the best possible case, I would say. Like, we have a lot of structure that is interesting. And yeah, this is what we are going to see here. Furthermore, we are going to compare this to the more well-known approach of Brzezinski-Majid, and then also see examples of this situation. Okay, let's start. I will first start with the braiding because I feel that this is the part that is not very well known. So let's talk about this. So we start with a quantum principal bundle, so a Hopf-Galois extension, B in A. And so if we just look at this ISO, we have on one side, we have the balanced tensor product, and here we have A tensor H. Now notice that on A tensor H, we have a natural algebra structure. We can just use the tensor product multiplication, and this gives us an algebra structure on A tensor H, while this is not the case on the balanced tensor product. So it is not clear how to multiply here. If you try to just take the tensor-wise multiplication, this is failing because this won't be compatible with the balanced tensor product. However, we can simply use this isomorphism, that is an isomorphism of vector spaces, and we can declare it to be an isomorphism of algebras. We can do that. And so in other words, we can pull back the tensor product multiplication on A tensor H to the balanced tensor product this way here. And what you get is an associative product on A tensor B A. This product then looks like this. So I take two tensors here and I multiply them. What I get is something that I write here as sigma, where the sigma is an operation that is written here. It doesn't really matter what it is, just saying that you get something here. And this something turns out to be a braiding. And that's something I found very interesting because I've never seen this, and it's very simple. It's a very simple way to get a canonical braiding. So there the statement would be, first of all, if I look at the balanced tensor product with this multiplication, the canonical map is automatically an algebra morphism, and also the translation map, so the inverse of chi, is also an algebra morphism. Furthermore, this sigma is an isomorphism in the category of B bimodules, and it satisfies quantum Young-Baxter or the braid relations. So it is a braiding. And furthermore, we have braided commutativity of A, meaning that if we braid and then multiply, is equal to just multiplying in A. Okay. So this is a, yeah. Yes, so notice that the canonical map is left linear. Because if we go back, if you see what the canonical map is here. So you see this is a left linear map. So also the inverse of chi will be a left linear map, which means the only information you really need for the inverse is a map from H to A tensor B A. So kind of chi -1 would simply be to nothing to the first tensor, and then this tau. So, okay, so this is the story of this braiding, something that is in a non-published paper. Okay, so the next step would be differential calculi that we have seen very well in the pre-seminar. So just recalling a little bit. So if you start with a Hopf algebra with coproduct at delta, again we use the Sweetler notation for the coproduct. We have the co-unit epsilon and the antipode s. We usually write H plus for the kernel of epsilon, and pi e is the canonical projection of H to the kernel. Okay, we have seen that a first order differential calculus on H is called left covariant if there is a coaction, in this case a left coaction on the one forms, such that D is a left collinear map. Yeah. And okay, I also want omega 1H to be a covariant bimodule, so the module action has to be compatible with this coaction. Yeah. In this case, we write lambda 1 for the co-invariant one forms under this coaction. We have seen that there is this classification theorem, Voronowicz, telling us that left covariant calculi on H are in one-to-one correspondence with right ideals in the kernel of epsilon. And there's a nice way to implement this theorem. It just means that the bimodule of one forms is isomorphic to this H tensor lambda 1. And lambda 1 is the quotient of the kernel of epsilon with I. Now, this I we have here. And you can see this I also as the kernel of the Cartan-Maurer form, something that I write as var pi. And it's basically just written in terms of the antipode and the differential on H. And we've also commented that this calculus is bi-covariant, so there's an extra coaction on it, if and only if I is closing under the adjoint coaction. Okay, this is the first order. We have seen that we can always go from first order to higher orders. And one way is using the maximal prolongation. For differential forms on Hopf algebras, there is a really nice way to implement this. This is what's written in this theorem here. So if you take the maximal higher order calculus corresponding to this left covariant first order differential calculus, we can also write the higher order forms in this way, where now the lambda bullet is like the exterior algebra of the invariant one forms. And as an algebra, this lambda bullet is just the free algebra, where you quotient out just these relations here, which is basically telling you that the Cartan-Maurer equation holds on your higher order forms. Yeah. Yeah. Okay, so you're saying
it's older, yeah. It wasn't a shell level, no.
Okay. Yeah. Okay, thank you. Yeah. Good. So now we have these forms on H. What is it? So first of all, probably this is also not the first reference, but I mean, in this book you can find it written down in a nice way. You can see that the coproduct that you have on H extends in a natural way to this higher order forms. So you can extend them as a morphism of differential graded algebras. Yeah, and this works automatically if you take this maximal higher order calculus. So there's a short notation that we're going to use with these brackets here. And of course, keep in mind that since this delta bullet is a graded map, so this means if I take an N form, then this will be a finite sum where I have components in K form, tensor L form, where K and L have to match to give you N.
And is this a genuine coproduct?
It is a coproduct. We are going to see this in the next proposition. Very good. Yeah, so the statement is, so using this, your higher order forms, so first of all, they form a bi-covariant higher order differential calculus, but they are also a graded Hopf algebra, where we use exactly this morphism of differential graded algebras, extending the usual coproduct. Epsilon is almost setting everything to 0, just in the 0 order. We have some non-trivial things. And there's also a nice way to write the antipode. And it's basically just making it an anti-morphism of differential graded algebras. By definition, you just have to prove that it is well defined. And in this way, you get a graded Hopf algebra. Again, we can see this as some functor from algebra to differential graded algebra that preserves Hopf now. Yeah? So now we have a DGA that is also a Hopf algebra. Very nice. Good. So now coming back to the quantum principal bundle, we want to do also something with the base and with the total space. So what we have to understand what are good differential forms there. So we keep this calculus we have seen on H. And there's a proposition that tells us we can find, just from this data, we can get a differential calculus on A, that will be the vertical forms defined in this way. So we take the invariant forms on H. This lambda bullet was the invariant forms on H. And then we just take the tensor product with A. Note that the calculus on H we have seen is isomorphic to H tensor lambda bullet. While here we just make the definition that those vertical forms are A tensor lambda bullet. And we can show that this is in fact a differential calculus if we take the following wedge product and differential. So the wedge product is basically just you want to multiply the A part and you want to multiply the invariant forms. And for doing this, the A prime has to pass through theta. So what you can maybe recognize here, this is the Jeter-Drinfeld grading that you apply here, and then you simply multiply and add wedge. You can show this is really an associative product. This is good. While for the differential, what's interesting is that you get two terms here. The first term is the easy one. It's just you take the differential on the form, while on A, you first use the coaction, so that you get something in A tensor H. And then you take the Cartan-Maurer form that, if you recall, was a map from H to the invariant forms. This was a way to get an invariant form, and you wedge. And you can show that this is really differential. So this gives you a differential graded algebra. And in order to show that you have also the subjectivity property, you heavily use that B and A is Hopf-Galois. Otherwise, this is not working. Okay, very well. This is what we call the vertical forms on A. Okay, so let's come to one of the central definitions of this talk. Djurjevic calls now any differential calculus on A complete if the right H coaction extends to a morphism of differential graded algebra. Very simple definition. We have this coaction, we have these forms on H fixed. And now if we take some forms on A such that this is really the extension of delta A as a DGA morphism, yeah, this is what he calls a complete calculus. And in this case, we call the forms on A the total space forms. Okay, also here we're going to use some short notation that says, okay, this graded coaction, we're going to see that this is a graded coaction. We just write it as omega 0 tensor omega 1, also keeping in mind that this is a finite sum, and this will be a direct sum actually of some K form tensor L form if we plug in an N form or a K plus L form. Yeah. Good, so this was vertical forms and total space forms. Yeah, some statements about what follows from this definition. So if we take such a complete calculus on A, First of all, the total space forms, they are a graded four-module algebra corresponding to this graded Hopf algebra that we have seen. So this is, again, this functor that says we start with a co-module algebra, and now the corresponding differential graded algebras, they are, again, a co-module algebra, but in this graded category. Okay. Furthermore, you can show that you get a surjective morphism of differential graded algebras from the total space forms to the vertical forms. So meaning you can always understand the vertical forms as a quotient of the total space forms. And the nice thing, or not so nice thing, you can write down this morphism explicitly. It's written here. I mean, it looks a bit creepy, but it's really just, we just use the coaction, differential, and wedge product. And maybe you can see that if you look at this for one forms, so if you plug in just a one form here, this is exactly the vertical map that we have seen in the previous talk. So it gives the correct thing. Good. The last thing I want to mention here is that vertical forms are in particular a complete calculus, meaning that the coaction extends to a DGA morphism on the vertical forms. And you can furthermore show that the graded coaction that you get on the total space forms and the graded coaction you get on the vertical forms is intertwined by this projection pi v. So it's really just projecting the structure on the total space forms to the vertical forms. Okay, and as a very special case of this, you can see that in particular, the total space forms are a right-age covariant differential calculus according to the definition we have seen in the previous talk. Good. Yeah, so we had vertical forms, now horizontal forms. So what is this? Starting with a complete calculus on a quantum principal bundle. Horizontal forms are just the pre-image of this extended coaction of this space omega bullet A tensor H. So those are all the total space forms that are mapped to a trivial fiber under the graded coaction. That's how we can think of it, and that's why, I mean, geometrically you could call it horizontal. Classically, it's the correct thing. And anyway, so that's this gives you a graded space, and you can even show this is a right-age co-module algebra. But it's not a differential graded algebra, meaning that the differential is not closing, or I should say it's also not, yeah, the differential is not closing, and there is a nice interpretation of this, but I'm not going to talk about it here. So, yeah, okay, horizontal forms, and I think now really the last thing, and then, so I'm sorry for all of these definitions, but we're almost done. It's still missing what are base forms. So what is happening on the base algebra? And there, again, a very simple definition. We just take the base forms to be those total space forms that are invariant under this extended coaction. Also, this reflects, yeah, very nicely the definition of B. That was just the invariant elements under the action, under the coaction. So the base forms should be the forms that are invariant under the extended coaction. You can show that this will give you a differential graded subalgebra of the total space forms. There's one drawback that says this might not be a differential calculus on B. So it might happen that it is not generated in degree 0. However, in all the examples that we looked at, it actually is. And in this case, this is just the usual pullback calculus that you would expect. Okay, Atiyah sequence and Brzezinski-Majid. So one more good thing about these Djurjevic calculi is that you automatically get the Atiyah sequence for free. So you can show that with this datum, you can write down this sequence. We know what horizontal one forms are, vertical one forms are, total space one forms are. We have this pi v map, and almost by definition of what we did, this is an exact sequence in the category of right-age covariant A bimodules. So in the literature, you would look at this a little bit the other way around. You would start with the sequence and then try to understand what kind of calculi you have. So there's this very famous paper from '93 that says, okay, if you take a right-age covariant calculus on a right-age commutative algebra A, then you would call it a quantum principal bundle. So here I should say a la Brzezinski-Margit. If, first of all, the vertical map that you can write down here makes sense, it might happen that it doesn't. And if the sequence that you have here, so this Atiyah sequence, is exact. And in this case, you call A dBA the horizontal one forms. So how are these two approaches that we have seen related? You can show that the Djurjevic one is more general, because if you have a quantum principal bundle a la Brzezinski-Margit, you have that the one forms, so the total space one forms, are complete in first order, so meaning the coaction extends to the first order. And the other implication is almost true. So if you have first order completeness, then you get a quantum principal bundle a la Brzezinski-Margit, if and only if the two horizontal forms are equal. So in general, the horizontal forms on the left are just a subspace of the right. But okay, if they are equal, then really the two approaches are the same, or I should say, this one here is like a first order version of the Djurjevic one. And I should also say that in all cases, in all examples that we looked at, the two approaches were equal. So the expectation would really be that this is a first order case of Djurjevic. Okay, so what else do we get from these calculi? So we have seen that everything goes through very nicely to differential forms, like all of the algebraic properties. And the one good thing is that also the Hopf-Galois property goes through. So given a complete calculus, we can write down the canonical map, but now for the graded coaction. So it's really using the same definition we have seen on the algebra level. I just use this extended coaction here rather than the coaction, and of course the wedge product instead of the product. So you can show that automatically without asking anything else. This is a bijective map. So for any complete calculus on a quantum principal bundle, you get that this is a graded Hopf-Galois extension. The way to show it, or I mean, the way how we showed it was you have to make sense of the extension of the translation map. And you have to show that this is well defined, which is not easy. So you have to do some computation, but it works out. And okay, I'm going to skip the details here, but just saying, okay, you have to make sense of this extended translation map. In first order, it looks like this. So you get two terms that it's, yeah, okay. Anyway, that's how you prove it. So again, nicely telling us that this functor preserves this property of being Hopf-Galois. Okay, also the braiding goes to the forms. So recall that we have this nice canonical braiding on A, written here in terms of the translation map. And this extends to a braiding on the total space forms, now over the balanced tensor product over the base forms. In particular, so here it's a bit tricky because you can actually move forms from left to right if they are base forms. So this means that, for example, if you want to braid two one forms, it does not only give you like something in one form tensor one form, but it could also give you something in two form tensor zero form and zero form tensor two form. It's just like graded map. And as we're going to see, this is actually happening in some of the cases. Yeah. Okay, so we write down this thing here. There are some signs, wonderful, but it's basically the same formula. It's just using this extended coaction and the extended translation map. Then you can show this is, so the extended canonical map and translation map, they are morphisms of differential graded algebra. You can show that this delta bullet is an isomorphism in the category of omega bullet B by modules, and it satisfies quantum Yang-Baxter. So it is a braiding in that sense, yeah. And furthermore, the total space forms, they have some graded braided commutativity. In that sense, you can first braid and then wedge, or wedge, and it's the same. And note that, so you would say, there's a sign missing here. The sign is incorporated here. So classically, it's really this statement that you have this graded commutativity of forms.
And so, Thomas, just to be sure, this is the work of you and Antonio. This is not in Đurđević.
It is in Đurđević paper. It's an unpublished paper, and I mean, we wrote an algebraic proof that is maybe a bit simpler to understand, but all the statements you can find in this unpublished paper. Okay, so this is about the braiding. Examples, yeah. Maybe now, since we have gone through all of these very dry definitions, let's see some examples. Okay, so let's start with something simple. Let's take a Galois object, just take H. So we know, since H is a Hopf algebra, if you take as coaction, so if you take on H an H coaction, that is simply the co-product, the only invariants you can have under this coaction are multiples of the unit. So here B would just be the ground field K. And so in particular, you would call this a quantum principal bundle. Yeah, that's kind of the easiest case you can think of. So here, if you start with a bi-covariant first order differential calculi, we take the maximal prolongation to higher forms. As we have seen in this lemma, the coaction, the coproduct, which is the coaction in this case, canonically extends to higher order forms. So here, automatically, we get a complete calculus in our according to our previous definition. So this works fine. Horizontal and base forms are trivial, you could show, while the vertical forms coincide with the total space forms that is now just omega bullet H. Yeah, so this is kind of an example where we have a trivial base, and yeah, that's it. Example of a quantum principal bundle with trivial base. Okay, in this case, you can nicely write down the inverse of the Hopf-Galois map, just using the antipode of the graded Hopf algebra. And in this way, we can write down the braiding nicely. You see that on the level of H, yeah, this is exactly the Jetta-Drinfeld braiding. This is what you get. While on the level of forms, you get some kind of graded Jetta-Drinfeld. So this is again Jetta-Drinfeld, but with some sign, and yeah. Good. And note that this is a true braiding, so it's not a symmetric braiding in the sense that it doesn't square to 1. No. So this will correspond to a true braided monoidal category, not to a symmetric one. Yeah, sure. So whole class where this applies, even though it's kind of trivial because here the base is trivial. Okay. Good. The next one is the 2 torus. And we've also seen in the pre-seminar. Just recall you that here we have some generators U and V with their inverses, and VU equals e to the I theta UV for some theta real number. This can be seen as a comodule algebra where we have a circle coaction, and we simply map U to U tensor T and V to V tensor T minus 1. You can see that this is a Hopf-Galois extension that is even faithfully flat, but okay, it's not really crucial here. The corresponding co-invariant subalgebra is again a circle. So all the combinations of the product of U and V, and you have a cleaving map. We've also seen in the previous talk what this means. So this is the algebra side. What kind of differential forms do we take here? One choice that is nice is that we take the differential calculus, so the first order differential calculus, spent by some du and dv with some commutation relations that are induced from the one on the algebra. So we have some e to the I theta if we move some v to the left of a du and so on. We also have some two forms as the span of the wedge product of du and dv and no higher form. So the top form is the du dv. While on h, the circle, we just take the classical differential calculus, classical. So just one forms, no higher forms. So we have shown that this is an example of a complete calculus. So meaning that the coaction extends to a DGA morphism, and as the base forms, you get the usual pullback calculus, just what you would expect. Here, just mentioning part of this was known. So it was known that you have a well-defined coaction on the one forms and the two forms. Also, the vertical map was known. We showed that also this map here, so the vertical 1-1 map that mapped the two forms to one form times the one form, also makes sense and in a nice way such that you get an extension as a DGA morphism. Okay, so that's an example. How does the braiding look like here? On the next slide. So yeah, there are many cases to look at, but for example, if you take any element f in the torus, and let's say the generator u, if you braid u and v, you get here some adjoint action of u, and the same with v. While on the higher order forms, I mean, I listed some of them here. You can see all of them in our paper. So it's actually not super difficult. You can see that it's basically just this theta commutativity. So if you have some du and u, nothing really happens. It's just the flip. But if you have du and v, you get some theta. You know? And similar if you braid like two forms with functions and so on. You know? All of them with the correct sign, of course. So here you see you get a minus because it's one form with one form, while if you braid a two form with a zero form, there's of course no sign. Notice that in this case you get a symmetric braiding. So you can show that, yeah, here you get a symmetric monoidal category. Okay, next example, SU2, so SUQ2 and the Podlesh sphere. Also something we have seen previously. So just recalling very briefly, we take SUQ2 generated by alpha, beta, gamma, delta, modulo a lot of things. We have a circle coaction given by the matrix co-multiplication. Also here it's very well known that this is faithful flat Hopf-Galois, and that the subalgebra of co-invariant elements is the Podlesh sphere. What differential forms do we take here? So we take a 3D differential calculus on SU2, something that Ray likes very much. So I'm pleased to present this here. Yeah. So here we have three invariant forms. So E plus minus and E0. Take the left span with some relations that I don't give here, but they are not so difficult. There are also two forms. So this is E plus minus wedge 0 and an E plus wedge E minus. And you have one top form that is like the wedge of all of them. Okay, that's the calculus on A. While on H, again, you have just zero forms and one forms, but here we take some deformation of the classical differential calculus. Namely, we take one where we can move a t from right to left with the cost of a q squared. So if we do this, we also showed that this gives a complete calculus with the Podlesh, so the calculus on the Podlesh sphere being the usual pullback calculus. Also here, a lot of things were known. So it was known that you have all of the coactions and that the vertical map exists. while we show that you can also make sense of this vertical 1-1 map and the vertical 2-1 map. Note that there are no higher vertical maps because, yeah, like we don't, so we have only 3 forms, and on H we have just 1 form, so there's no combination that would be like omega-1 tensor omega-2. It's simply not there. Okay, how does the braiding look like? So on the algebra level, things are very much mimicking the commutation relations. So let's say if you want to braid alpha with alpha, nothing happens. But if you want to braid alpha with beta, you get a q minus 1. Yeah, and similar with alpha and gamma, it simply gives you the commutation relations that you also know on the algebra level. Yeah, so for example, the most difficult one is the one of alpha and delta. This gives you the 2 terms that you know very well. So on forms, it's a bit more complicated. In particular, here happens something that I mentioned, that it could happen if you braid a 1 form with a 1 form. So you get 1 term that is 1 form tensor 1 form, but you also get a term that is 2 form tensor 0 form. Yeah, so it's really not a braiding in this sense that it maps only 1 form tensor 1 form to 1 form tensor 1 form. It's just a graded map, so you have all possible combinations. But note that in the classical limit, so if q goes to 1, this term vanishes, and you get the correct classical limit. So things still make sense. That classically you just get the graded flip. And yeah, I mean, I've listed some of them. If you want to see more, you can look at our preprint. And here, just mentioning that on the level of algebra, it's a symmetric braiding, while on the level of forms, it is not. Okay, we come to the last example. I think then I'm done. So that's another class of examples that is based on this trivial and cleft extensions. So again, starting just starting from a right H commodule algebra A. Now we look at B, the co-invariant subalgebra. In this case, as we've seen, we call B in A a trivial extension if we can find a convolution invertible comodule algebra morphism J, and cleft if this one is just a comodule morphism. So we don't ask it also to be an algebra map. And then there's this nice hierarchy that tells trivial implies cleft implies Hopf Galois. Furthermore, Doi and Takeuchi showed that these cleft extensions correspond one-to-one to cross-product algebras. I'm going to show you in a second what a cross-product algebra is, but so just saying there's a nice algebraic way to think of cleft extensions. And in this picture, trivial extensions correspond to something that's called a smash product rather than a cross product. So a cross product algebra is the following. So now take B as just an algebra. So there's no A, there's just an algebra B. And H is a Hopf algebra. And now you want some map from H tensor B to B. Think of it like an action, but it's actually not an action. It's what some people call a measure. So here you just ask that if you act on the product, this is given by the co-product acting on the single elements, and the action on one is the trivial action. What you also need here is this map F. That is a convolution invertible to co-cycle with values in B. Okay, there are some properties that it has to satisfy. I don't mention them here, but think of it, it's a to co-cycle. That is mapping to B. Given this datum, you define the cross-product algebra that I call here B cross FH. In this way, so it's just the tensor product as a vector space, B tensor H, but you have this multiplication, this product here, that says, okay, I would like to multiply the two B's and the two H's, but the B prime has to pass through H. So what you get is this, okay, H1 kicks B prime, yeah. And then you have also some contribution of the co-cycle. So this has values in B, so you can multiply it on the B side. And it turns out that by definition of everything, this is in fact an associative unital product, and you get an algebra, the cross product algebra. If you take the co-cycle to be trivial, so just epsilon tensor epsilon, this is this mesh product. And in this case, the dot here is an honest action. So then also here, this product becomes easier because this is really just B, H1, B prime, H2, and H prime. And okay, this theorem of Takeuchi then just says that, okay, those algebras, they are the same thing as a cleaving map. And it's a very nice proof to see that this is in fact true. And okay, some way how to think about it in the quantum principal bundle framework. So if we say Hopf-Galois means quantum principal bundle, then the cleft ones are those that are locally trivial or even globally trivial, because it's kind of telling us that our algebra is isomorphic to something like base tensor fiber. Yeah, it is telling us that here we really have a decomposition into base tensor fiber with some convoluted product, yeah, but still it has this what is called normal basis property. Okay, for those algebras, we also found some Djurjevic calculi. First of all, we need this definition that says a first order differential calculus on a B, like in the previous slide, is called F twisted if this measure is compatible with the differential forms. Yeah, so if it extends to the one forms in a way that is very natural, so just compatible with everything. And you also want that the composition of D with the two co-cycle vanishes, so that D somehow doesn't see the image of the two co-cycle. Notice that in the mesh case, this last property here is mute, because if it's just epsilon tensor epsilon, every differential vanishes on the unit. So here you ask nothing, but in the general cross case, that's an extra. So yeah, last year with Chandra, I proved that given such an F-twisted calculus, you get a natural differential calculus on this cross-product algebra that you write in this way. So basically, you just take the tensor product of omega 1b with H plus B with omega H, some bi-covariant calculus on H, with appropriate bi-module structures that somehow mimic this this cross product. So they will look a little bit like this here. Just now, some of those guys will be one forms. Yeah? And the differential will be just the sum of the differential on B and the differential on H. So that's a way to get a lot of differential calculi on all of these cleft extensions. And what we showed more recently is that those calculi are all Djurjevic calculi. So they are complete calculi, but the correction extends to DJ morphism. If you extend this first order differential calculus in a suitable way, I skip all the details here, but there's a natural way. Oh, there's an H missing, sorry. There's a natural way to extend this to higher orders, and then you see that all of what we've seen previously goes through in this case. The base forms are the usual pullback forms. The vertical forms are now just B tensor the forms on H. Horizontal forms are all of the base forms, tensor H. And the Djurjevic braiding can also be written down explicitly in this very horrible formula. So I don't know, looking at it like you wouldn't guess this, right? It's not something that you say, yeah, sure, this is a braiding, but according to this general framework, we know that it is, and it even extends to one forms. And yeah, so another class of examples. And yeah, I think with this, I finish. Thank you.
Very much for a great talk. So do we have questions, I guess, first of all, from the audience?
For your non-commutative torus, can you say anything when the theta is irrational?
No clue.
Okay.
Sorry. So here, so I think you missed the first slide where I said like something. Okay, so here we are very modest. We just want to work in the algebra framework, and later on, of course, you would like to have a C-star algebra or a spectral triple or whatever. But this is really modeled on the algebra level. So I haven't thought even a bit about this. Sorry, I cannot help you.
FYI, I thought the chat popped up in the middle of. Oh, okay.
Okay.
Some more questions from, yep.
Do I need it?
Yes, because it's
Just a quick question. Do I understand it right that the whole data of Dirichlet calculus depends only on the trading?
I would say it's a consequence, like something you get naturally from the setup. Yeah. So it's not that it depends on the braiding. I wouldn't say that.
Well, that's parameterized by choice of trading.
So if I go back to the is it even here? Can I use this? No. Okay, I do this. So debraiding is automatic. Like every time you have a Hopf-Galois extension, you get a braiding for free. That's in this one here. Just pulling back the product on a tensor H, you get this braiding. So it's not depending on the calculus.
Yeah,
it's
so
just that the question, maybe this is your question, if it extends to differential forms.
Yeah, basically what I was asking is if you can always recover the Hopf-Galois structure just from the braiding.
Okay, other way around. So if you
recover high from
given a braiding, can I get a Hopf-Galois extension?
Yeah, you had the translation thing. So I was wondering if this translation thing allows you to state everything just in terms of braiding and recover high.
Okay, so you would say, for example, if I have the translation map here, and if I would know this is an algebra morphism with some product on a tensor BA, does it follow that B and A has to be Hopf-Galois, something like
Well,
this?
it's more like, is it possible to give a, well, I guess it's possible to give a definition of a Durdevich braiding without appealing to the notion of Hopf-Galois extension. Durdevich braiding is a braiding which is a linear on the left, plus some other conditions that allow you to get
I'm not sure if you can do that because I mean it's an honest braiding. It's a usual braiding just for the special case when you have an algebra that is a Hopf-Galois extension. So it's just an example of a braiding. I don't know how to make a general definition out of an example. I don't know.
Yeah, well, I mean, it has a very special property that you mentioned. It has to be a linear. One of the
okay. So like you are asking, for example, in this category here, this B bilinear. So if I take the category of B bimodules, if I take any braiding there, does this somehow correspond to?
Yeah, can you figure out whether it comes from Hopf-Galois?
Okay, it's an interesting question, but I don't know. I mean, you would need at least a comodular algebra, I think, and then I don't know. I cannot answer. Sorry.
I have to recall when I was. Okay, so the question is, what is the abstraction which obstructs the existence of extension from calculi to complete calculi? So, in particular, degree wise. So what does it mean? What's that object on for degree 1, for degree 2? Do you know it?
Yes, so I can say a little bit about this. So in first order, as we have seen, it's really just asking these two things, like is the calculus a covariant calculus? And then can I make sense of the vertical map? If you can ask those two questions, and if the answer is yes, then it extends to the first order. And then if you know a little bit more about the higher order forms, namely here, if you take the maximal calculus, then the extension to higher orders is automatic. This you can show if this is the maximal. Yeah, in that sense. But if you take something else, I mean, if you take any calculus, you would have to check order by order.
Cannot be very this question extending in terms of some algebraic invariance of H itself.
Okay.
I suspect this is a question.
I mean, it would be some kind of, so I think you could phrase it in some kind of higher ATIA sequences, like for the vertical map, it's an ATIA sequence, and maybe you can write like higher versions of the ATIA sequence. I'm not sure how this would correspond to some invariants or some properties of H. I don't know, but I expect some sequences that have to be expected.
Okay, and not yet. Another question: what is that? You mentioned it on one of the last slides. The F twisting. So classically, if one has if there is, I don't know, vector bundle on some manifold, so what does it mean to F twist?
So your question is about the cross product algebra or about the differential calculus? Both. Okay. So first for the cross product algebra. So exactly right. So produce another realization. Yeah, so it's kind of, it's a trivialization, but you don't get the tensor product multiplication. Like you would get some extra co-cycle on the group, like twisting your multiplication classically. Yeah, so it would be like a modified multiplication. This bundle one with the probabilities operation with another so are they topologically everyone, for example, or is it for geometry? Yeah, so I think there's this notion of when cross product algebras are isomorphic, and maybe Andre knows this. I'm not sure, but yeah, there is some notion of twisting cross product algebras, and probably then you can talk about equivalence classes in that sense. But I'm not sure. I don't know this. Yeah.
Okay, I'm gonna ask some question myself. So for the braiding that you have, which is amazing that this pops out. I mean, is there some connection like at the degree 1 level to bimodule, the braiding come from a bimodule connection in examples?
So that's an excellent question. It's something that we also tried to figure out, because it's quite natural that if you have given this braiding for free, of course, the next question is what are bimodule connections? Yeah, we didn't work this out, but I expect there to be a bimodule connection too.
Yeah, because I mean, if you look, for examples like Heckenberger, Kolben, whatever, then there aren't that many braidings there. So
the only thing that could go wrong, as you were seeing, it might happen that braiding a one form and a one form, you also get something like 2 form tensor 0 form. Yeah. So
wow.
And so you've seen this for the
I missed it.
SQ2. So here, if you look, you braid those two, and you get this, which is the classical flip with the minus sign. But then you have this term that is like here you have a 2 form and there's a 0 form. Yeah.
Okay, this I missed.
This guy vanishes.
Yeah.
But so it's not straightforward, because it's not really a braiding of omega 1. It's really a braiding of omega bullet.
Yeah, it's not a graded map.
It is a graded map, but it's
it is because it preserves the degree. Yeah, sure. But it's genuinely for the whole calculus.
Yeah, so it's a braiding of omega bullet rather than omega 1.
Yeah,
that's the thing.
And is there some conditions that one could put on, or extra restrictions in order to make it? Because what I would like to do then is to look at the Nichols algebra associated to the degree 1 part, and then try to construct the maximal prolongation as the Nichols algebra associated to this. But if it's messing up the degrees, then that won't work.
I mean, you could kill all of these weird terms, of course, but
But
I
then-
guess then it's not a braiding
Yeah,
anymore.
yeah,
so
yeah,
maybe
yeah,
you would
yeah.
lose something. I don't know. So it's
Yeah.
really something you would have to make sense of these strange terms that
Yeah,
you might get. But apart from it, I think it should be possible to use it either for bimodule connections or Nichols
Yeah.
algebras or whatever.
But then, in the classical situation, though, it reduces down to the usual flip.
Yes. So
Yeah.
you can see here also.
I mean, sure, in this
system
example, but in general, for like a commutative manifold, and you do all of this.
I don't know if we can have such a strong statement, but like in all the cases that we looked at, where there's some Q
Mhm,
deformation, you see that when Q goes to 1, you get
Yeah.
back the usual gray
Yeah.
flip.
Okay, very interesting. One small question I have as well is that what isn't this is going to be a question to Antonio as well? The algebra B, the subalgebra of the non-commutative torus. What's that classically? What's the geometric motivation?
So it's another
circle or something?
another circle. So
Yeah.
I'm not sure if we can understand it as the torus being, like those two circles. I'm
Yeah,
not sure.
yeah. Okay, so maybe it's one of the
Because
circles.
if you think of the U1 action, like what does it do? Maybe it's like turning in some direction. Then like the inner circle would be the one that is not touched by it. So something like that. This could be the.
Mhm. Okay. If you have any questions online, just unmute yourself and go ahead. Or not. Then
It's simply a computation, and yes, so I don't see any deeper reason.
for questions from the audience? No, appears not to be the case, so we'll thank Thomas again. Next week's talk, we have an external speaker. It's okay. So next week's speaker is Jan Grabowski from the University of Lancaster, or Leicester. Leicester, yeah. And he will, Lancaster, I got it right the first time, good. And he will speak about cluster algebras. Yeah. So hopefully we'll see you all there.